Told me to talk about anything I wanted. So you guys are the victim of the random choices I have made. Thought, appreciate a little bit the beauty of the science, beauty of the engineering, and the human mind coming up with some of these extraordinary concepts. So let me show you a few of my favorites, and some of them are related to Bell Labs, where I'm from, unsurprisingly. So we as human beings, we love the electromagnetic spectrum. We're obsessed with it. Everything we do is somehow connected to this thing. From all the way from the smallest wavelengths to the largest wavelengths, we find a way to manipulate and use advantage. So for example, we take a big set of antennas, we space them at a certain, and we put those spacings according to the wavelength of the light. Good? According to the wavelength of the light. You want me to use this? Okay, so let me switch over. No worries, there's always some technical difficulty anyway. Okay, good? Better? All right. So we take a bunch of antennas, we space them according to the wavelength. It turns out that they can interfere with each other in such a way that we can steer the beam in a certain direction. And there comes a phased array. Gets a Nobel Prize, 1909, by manipulating the way waves interfere in free space. Or you can take an antenna, face it toward the sky, read signals you cannot interpret, and for a long time think that these signals are because of the pigeons that were living in the antenna. That's actually what they thought. They eventually discovered that this is actually the signature of the birth of the universe, and discover cosmic background radiation. Again, Nobel Prize, you win that. That one is at Bell Labs, 1978. Or you figure out that there's actually a way to trap matter using photons and hold it suspended so you can have individual atoms that you can excite. It becomes a foundation of a lot of quantum physics work called the optical tweezer, also Nobel Prize at Bell Labs in 2018. Or we figure out that we can actually manipulate the amplitude and the phase of light, trap it inside thin strands of glass, make fiber optic communication coherent communication, and push a staggering amount of data through the fiber. You get coherent optics, and the records of it is constantly held, again, by Bell Labs. Or you figure out that you can take a photon, put it through a semiconductor material, it converts back to an electron. You collect that electron, you array it into an array, you get a charge coupled device, you get a Nobel Prize, you invent the CCD. Or you figure out that if you hit matter with a particular wavelength of light, it elevates the energy state of the molecules inside of that matter, and they go to a higher state. But when they come back, they give you a signature, and that signature tells you about the chemical bond of that material. You discover Raman spectroscopy, and you get a Nobel Prize, not from Bell Labs, but it is a phenomenal thing in its own. Or you know that if you make matter tiny, small enough, be smaller than wavelength, that matter, that light can interact with it, and interesting filtering effects can happen. And if you can manufacture with precision, you make quantum dots. What's in all these TVs? And you win a Nobel Prize, the latest one, 2023. And of course, lastly, you also figure out that it is possible to look beyond diffraction limits of light by exciting matter in a particular way with UV light, and you can see the structures of atoms even in the 20 to 30 nanometer. You get superfluorescence microscopy. That's also from Bell Labs from 2014. I mean, these are incredible things in one slide. We're capturing a fraction of a human ingenuity. And that's what I want to partially celebrate in the talk. So let's talk a little bit about where we came out of, which is the pandemic. We talked during the pandemic so much about the collapse of our medical ecosystem, the hospitals. But nobody ever talked about the fact that our communication network survived. Almost overnight, all of us, all the species, changed the way we consume data. We changed our habits. We changed where the data was coming from. We changed what wireless network we were using, what optical networks we were using. We changed the way the clouds needed to interact and keep up with our demand. We had an exponential rise in use of some of the apps, overnight almost, and it all just worked. So yes, you should definitely appreciate your medical community, but you should also hug an engineer, because this is an amazing thing. If this had happened a decade ago, the pandemic would have absolutely crippled us. All the remote work, everything we do was built on our telecommunication infrastructure. So where are we going in the future with regards to that? Well, there's a lot of talk, obviously. Companies talk about what 6G is. Companies talked about what 5G they want it to be. And one of the things that is typically going to happen, or is estimated to happen, is that we're going to have a convergence of the digital and the physical world. So we want to digitize everything. We want to create digital twins. We want to have ARs and VRs within reason, of course. And the amount of data that we consume as human beings is just constantly goes up. And the majority of the traffic of the internet is actually machine to machine at this point. So the traffic is going to grow even beyond what we can perceive and what we can absorb. But interestingly enough, you look at all the presentations from Nokia's or Samsung's or anyone else and Ericsson who are talking about this, they always talk about different technologies that's going to go into the heart of these kind of systems. And a lot of them are still physical interface devices, but we cannot get away from that. We're always going to need devices to interact with the physical world. And that transition is where a lot of data happens and a lot of innovation has to happen. And then at the bottom there, we show that obviously our industrial enterprises, our different companies' enterprises internally, as well as our own consumers, they're all going to have to be transformed in some way. So this is a very, very big picture. And it's supposed to show that every aspect of our telecom network has to keep up with it in some way. So this is how we've progressed roughly from 1G, 2G, 3G, and so on. And everybody knows in our industry that the odd number Gs don't do well. Right? This has just always been the case for some reason. So now 6G is supposed to do well just by that virtue alone. And we'll talk a little bit about some of the aspects of 5G, but what people often don't realize is that a lot of the network infrastructure is not just on the cellular side, because you cannot just increase traffic and complexity of one part of your network. You have to do it across the entire network, because everything has to ultimately remain interconnected. So if I make innovations in my cellular infrastructure, I have to change my optical network to go with it, because ultimately this data has to come from somewhere and it has to go somewhere. And this is the case. Now there's a lot of discussions about how much bandwidth we want to use in our wireless network, how much algorithms of AI and ML can exist in the network, and how does that look like. And it's not the typical AI and ML that you see in large language models. This is a much more serious issue, because most of the things we do, which as a consumer absorb in the AI and ML, have no consequences of failure. But you cannot have that in places like a network infrastructure, because it has to work, otherwise it's a cascade failure. So it's a pretty serious problem. You can't just unleash AI into any network you want. Now, in the words of Feynman, all of these EM waves exist at the same time in this room, all over the place, and it's really the inconceivable nature of nature, as he described it. So what are we talking about when we talk about spectrum? Well, we just keep adding to it, right? We tend to never really remove anything. We may reassign it, but it's always a new band added into the infrastructure of our communication. So we have all the way at the low side stuff below 1 gigahertz, which is a lot of IoT devices. There's some 6G bands in there, and going all the way to beyond 100 gigahertz. And the reason we go higher and higher in frequency is obvious, because there's more bandwidth there available. Fractional bandwidth means more bandwidth is available, and therefore you can build things a little bit easier. But there's a big penalty to pay for that. So you never add a spectrum to remove another. You augment it. So all these systems now have to coexist and work together. Now we know, I'm sure a lot of you are familiar with the millimeter wave 5G infrastructure and the challenges with that. And the industry really chose to go after the hardest problem of 5G millimeter wave, which is handsets. That's the toughest problem in that space, because the channel is so unpredictable, because the antennas are small on the handset, and you need to close these loops. So we did a lot of study at Bell Labs, over millions of measurements of looking at what happens to millimeter wave propagation in a variety of situations, at street levels, in factories, in buildings. And it turns out something somewhat non-intuitive happens, is that it doesn't matter if you make your beamforming phased arrays at 5G millimeter wave bigger and bigger and bigger. At some point, the interaction of the beam with the environment, because the wavelength is so small, causes enough scattering that there's a diminishing return. So you hit a wall pretty fast. On line of sight, you'll always get a benefit. But in a room like this, it becomes pretty difficult. And that explains why, if you look at your phone, that the millimeter wave utilization of your phone is not very high, at least not yet. So where is sub-terahertz and frequencies above 100 gigahertz useful today? Well, it actually turns out backhaul is the primary application right now. In backhaul, we've had millimeter wave much, much longer people even knew what millimeter wave was. If you look at this global map, you see that in some countries, the utilization of microwave backhaul is very high. But in the United States, it's not that high. Do you know why it's not so high in the United States? Any ideas? It's because we have so much fiber, right? Microwave links are good when there is no fiber, because digging fiber is expensive. But we did put a lot of fiber in the country. So utilization of using backhaul is not as high. But in Manhattan, if I want to go from one building to another, and I want to send 100 gigabit per second, I cannot dig a fiber if it doesn't exist, because it will cost tens of millions of dollars to do that. So backhaul becomes really interesting for some of these distances. So as I said, this is the spectrum that backhaul uses. It goes anywhere from a few gigahertz all the way to 170 gigahertz. The majority of the work we do right now in R&D for creating backhaul is in the upper frequency range. I'll talk about that. But if you look at the bottom, up to about 44 gigahertz, we do 4,096 QAM modulations on two polarization, and that's 10 years ago, right? So that's how spectrally complex these things are, because they have to be very efficient in their deployment. They have to be able to carry a lot of data, because the bandwidth limitations, everything is licensed and it has to be maintained. The other thing people don't appreciate is that backhaul is subject to an extraordinarily difficult cost constraint. People think that these things can cost whatever they want, but we really have to count every dollar. And not only that, these things can be put in the desert, or they can be completely frozen in Antarctica. So they have to work from -40 to +85 ambient, which is almost getting into automotive territory in terms of qualification. So a very difficult market and a very competitive one. But at the very high end, you could get 100 gigabit per second over the air. And 100 gigabit per second over the air is that magic number, because it's a fiber over the air at that point. And then you can do some pretty interesting things with low latency and a big amount of data between 2 points. The range is going to be limited as you go to higher frequency. You can't do tens of kilometers, but in places where you need to deploy that link, there's no other way. So, how do we get there? And what are the adjacent technologies we're taking advantage of, even if you don't always know it? So this is a plot from TSMC. TSMC, of course, manufactures semiconductors down to single-digit nanometers now, and 2 nanometer and then 1 nanometer nanosheets, and that's going to continue to some extent. We're actually not really following Moore's law at the per chip anymore. And that's actually not because we can't make a transistor small. It's because we can't make the yield anymore. So if you put 100 billion transistors on a die, which we can do now, at some point, if we want to do 200, you can certainly do it, but the yield becomes so bad that the economy of the problem falls apart. So now we need another way, a leap for a factor of 10 with some other means, and that is packaging. Right? So semiconductor packaging is one of the most important areas in semiconductors right now, because it's the only way to go from 100 billion transistors to 1 trillion using chiplets, by combining multiple chips on the same package. That sounds really obvious. Well, of course, if I can't make a chip so big, I'm going to have to break the chip. But there are major consequences for doing that, because inside the chip, you can send digital data with big buses of data very close. You're not burning a lot of power to transport data from point A to point B, because they're right next to each other in the same semiconductor silicon. As soon as you want to pass something to another package, now you have to design for that transition. And that's where all the power goes. That's why SerDes, serializers and deserializers, and clock and data recovery circuits are in such high demand, because that's what determines the power consumption of these systems. So advanced packaging has to be able to enable that. And that's where the money is, right? The trillions of dollars of global investment in semiconductors and everything that's happening over many decades, a lot of it has led to being able to make extraordinary good packages. And us, on the RF side, take advantage of the advancements fueled by the economy of a completely different industry. No one's going to spend $10 billion advancing a package for backhaul radio, but we can take advantage of those tooling to build our circuits. Here's an example of a cross-section of an Apple Watch, right? So this is actually quite a few years old. And this is it's just an insane piece of engineering. If you think about it, right? If you wanted to propose this to anybody who wants to make a microwave circuit, they would laugh at you because it's too complex, it's too expensive to develop. But for an Apple Watch, with the economy behind it, you can do this. This thing has die-to-die bonding, it has blind vias, it has air cavities, it has passives built into it, it's folded over, it's just a crazy piece of engineering. But we can do it because the economy is there so we can take advantage of this. Sometimes advantages in our RF come from unlikely places. So this is the loss of a PCB trace between 75 to 110 gigahertz for a different finish on the PCB trace itself. So the PCB trace is made of copper, but you have to finish it with something for multiple reasons because it's exposed to air and it also may need to be soldered onto. So if you take the copper bare by itself, it's fine. But the issue is that as soon as you add EPIG or ENIG finishing on top of it, which has nickel in it, the loss becomes significantly more. But it turns out that people discovered EPIG, which is a palladium immersion gold process that doesn't have nickel in it. They developed it for the medical industry because nickel is quite magnetic at lower frequencies for MRI use. So they did that, had nothing to do with RF. But voila, you make it and you get quite a bit of signal back, loss back by leveraging the technology developed in a completely different industry. During the last Nobel Prize at Bell Labs, the ceremony for the quantum dots, there was a list that the Nobel Prize winners put out as things that they thought was very important. One thing on that list was a problem that is very difficult in your field might be very easy in a different field. And that's why this cross-pollination between fields is so important. Because you may be scratching your head trying to solve a problem with the tools you have, but it may be trivial in a different industry. So how do we design these circuits then at these frequencies? Well, it's a massive co-integration effort. We first have to design RFICs, which themselves are a challenge, but not as much as perhaps you may realize at these frequencies, because semiconductor processors are so fast now. And then we need to design the entire transition. Every micron matters. From at above 90 gigahertz or so, we flip chip it, we simulate it, and then we can make these individual little blocks. I'll show you what that looks like. So this is what a big 95 gigahertz phased array looks like. So this is a 384 element phased array. This is already quite a few years old, but it shows the limit of how far you can push printed circuit board technology. This is an organic PCBs, right? At the time when this was made, nobody thought this was possible. But we basically leveraged the packaging technologies that I talked about earlier to be able to put a semiconductor die with extremely fine lithography at this frequency directly on a printed circuit board and build a large phased array. And this, you guys know what this is? Picture at the bottom left. I always tell people that this is what my bank told me I could afford when they saw my down payment, but it's not that. This is the world's first phased array, and that's the picture of Braun. That is where we started. Right? That's the first phased array, and then you can see what we can do after just over 100 years. So if you want to look at the beam coming out of that phased array, how would you do it? Well, it turns out that at 95 gigahertz, because the beam is so narrow, you can shine that beam on an RF absorber and create a heat spot. And then you can look at that heat spot with a thermal camera. And you can see that spot warm up. It's a really weird feeling because you can put your hand in front of it. Right? So you can put your hand in front of this 95 gigahertz phased array, and you can feel a little warm spot in the palm of your hand, which is invisible, of course. But that's RF energy that is combined on that one spot. It's weird because you typically don't expect RF energy to behave this way because the frequency is so high. So it's more like a laser on your hand than it is like an RF radiation. And you can even see the sync pattern of the phased array on the absorber. And since it's a phased array, you can also draw shapes with it thermally. So we're drawing a thermal image using a most advanced phased array that we had ever built and was actually available at the time in Bell Labs. We had some time on our hands. So how difficult it is to close a link? Well, very difficult. At 250 meters, at a frequency of 150 gigahertz, the free space path loss is 124 dB. That means your signal is reduced by a factor of 2.5 trillion. Trillion. That's what you need to recover, and that's only at 250 meters. I mean, these numbers are insane. It's just because they're in dB, you don't appreciate how extraordinarily large these drops are. So every dB matters. So it turns out that you cannot really use PCBs effectively anymore, unfortunately, above 110 gigahertz. You need an entirely new packaging paradigm. So a few years ago, we started looking at glass. So we built all of our circuits above 110 gigahertz on glass. The glass is our package, is our substrate for interconnecting RF devices, is where we put our antennas, is where everything lies. And glass is an extraordinary material because it gives you the lithography to work with, it gives you the ultra-low loss, and you can use it in the same industry process you're using PCBs. So this is the whole radio on glass architecture that we've been talking about for quite a few years, and we've built a lot of devices on it. So here's an example of a few semiconductor chips that we've made and their glass package counterparts. At the bottom right, you see 64 RFICs on a single piece of glass. That is a 256 element phased array at 150 gigahertz. And you can see the size compared to the Apple Watch, that you can fit 256 antennas in that space because it's so small. You need to simulate this entire thing at once in an electromagnetic simulator with the models like this that occupy hundreds of gigabytes of RAM and take days to simulate at every frequency. Otherwise, you will never be able to capture all the nuance and the interactions of the signals on the material itself. It becomes quite a bit of a challenge. Here's an example of an FDD link. So backhaul, point-to-point backhaul, unlike 5G millimeter wave. 5G millimeter wave is a TDD system, so it's jumping between TX and RX on the same spectrum. But backhaul is a full duplex, frequency duplex system. So you have one frequency traffic going in one way, and an adjacent frequency, the traffic's coming back that way. So what you need is a diplexer to separate them. So that diplexer is actually inside of that glass piece. So the entire backhaul radio with the FDD function is on that piece of glass. And you can see the data on two sides, one going one way, the other one going the other way. This is at 70 and 80 gigahertz. This is common in backhaul. So we talked about all of this. So what does our network actually look like? If you want to step back and look at the network as a whole. Well, we have cloud, we have edge cloud. On one side, we have what we call essential fabric. This is the fabric of interconnectivity. It's what is our passive optical networks, is our backhaul, is our fiber communication, is our copper communication. All of that sits there. Then we have all of the functions that sit on top of this network, sensing functions that use the network, and I'll show you a little bit about that. So now you have all of these pieces. Now Nokia is an interesting company in that sense, because Nokia has fixed network assets, has optical network assets, and it has wireless assets. So all of these technologies are under the same company. So now we need to think about what we call a network of networks, because how these things interact with each other is an entire new way and an entirely much more complex way of optimizing the network, because they need to talk to each other in some way, and our customers need to be able to interconnect them. So there is a layer on top of that, which we call the unified network, which has some of the AI and ML algorithms on top of it to actually make sure that this whole thing is optimized. And there is so much you can do that you will lose sight of when you look at an individual part of the network. So for example, joint communication and sensing. This must be right within your playground. How do we use a 5G network or a 6G network in the future to simultaneously serve traffic to our users while at the same time actually be able to communicate as well? And this is possible. And this is done by piggybacking on the OFDM signals and interpreting the OFDM frames and extracting environmental data from it. It's kind of like a radar, but it's not using radar waveforms. And then with that, we can, of course, monitor all kinds of things, and the network will be able to scan its own environment. It will be able to report back many of the things it sees in its own proximity. It's like basically having a radar on every base station, or multiple radars on every base station. And for that, you can do things like intruder detection. You can look at the behavior of movement of crowds. You can aid cars in moving. And this is done without a camera, right? So it's not a system that is as privacy invasive as a camera would be in many situations. So it has an advantage in that space. Let's see if this video plays. So here's an example of it. This was shown in Mobile World Congress. This is a 5G millimeter wave system where there's a transmitter and receiver. It's transmitting 5G data like a regular network would, and at the same time it's tracking an individual. So this is not, it's very important to realize that the system is not jumping between communication and radar. It's doing it at the same time. Because if you go to any operator and say, give me chunks of time so I can sense the environment, they'll laugh at you, because that's not their primary business. So whatever you do, you have to pick it back on the existing system. And there's places where you can basically manipulate the environment in an augmented reality fashion by tracking individuals while they're receiving the cellular data. Right? There's no camera used here. It's all purely done with 5G millimeter wave signals. You can also throw AI in what has been traditionally a closed computational system, like transmitter and receivers, where equalization, channel estimation, and so on. And if you do that, bizarre things happen. So on the right side is an example of what the AI algorithm came up with for a constellation that optimized this particular link they were testing. Now, this is not any known constellation. This is not even probabilistic constellation shaping, which is a whole other thing that's still a closed loop system, closed formula system. So it will measure nonlinearities and distortions and unusual behaviors in the channel, and it comes up with some crazy looking constellation that happens to optimize the link. And if you can get the power and the latency of these systems to compete with traditional ones, you can extract more from your wireless network. It becomes more efficient. And of course, there's Cloud RAN. I won't dwell too much into it. Something we can certainly talk about separately. But Cloud RAN opens the ecosystem to other interesting ways of implementing. It makes the radio so much more important in a way, because the radio now has to collect all that data and send it to the cloud and then close the loop in there. It's a whole big topic. Hours of conversation can go in there. I just wanted to make sure that you're at least a little bit aware of it. Can we sense the fiber? It turns out you can. If there is a fiber at the bottom of the ocean, you can treat the fiber like a radar channel. Right? There's no difference between EM waves traveling through a fiber in the forms of photons if you want to build a radar. It's just a constrained radar channel. And it turns out you can do that. You can have a fiber that's going from here to France, and you can look at the signature, the environment, the vibration, the pressure, and the movement has on the fiber and extract that at the receive side and look at what happens to the fiber. You can do this at street levels. You can do this when there are construction. And with AI models, the team has been able to figure out if somebody's digging near a fiber, they shouldn't be digging, or if there is an earthquake, or if there is a change in temperature, or if there's a movement where there shouldn't be. It's called the entire fiber sensing. So you can sense even within the fiber and treat it like a radar system. You can cram data into fiber in ways we would never have imagined. You can create what are called multi-core fibers, or put multiple modes in a multi-mode fiber and get to just insane levels of data. Right? In a multi-core fiber, they've managed to cram in 321 streams that add up to 1.77 petabits per second in a single strand of fiber. Right? Commercialization is obviously a bit further away, but it shows that even the fiber channel can be used in spatial multiplexing beyond ways that we thought was possible. We're also sending an LTE to the moon to help the aliens. We're also doing this because if you build a network infrastructure, in the process of learning what happens to it in space and building the hardware for the efficiencies required, that learning process has applications because you're engineering, constraining yourself into a very difficult environment. And this is a work that's done in conjunction with NASA that you can certainly take a look at. It should be quite interesting on its own to see how we can enable this network on different planets and what are the technological challenges of that. So since I'm from Bell Labs, at the very end, I want to tell you something else that's pretty important to me. And that's, of course, the aspect of education. So let's start from this. This is me holding the world's first transistor, which was invented in Bell Labs during a cleanup they were doing when they were moving the museum. So I managed to hold it. You can see I'm wearing a white glove. This is now quite a few years ago. It's much smaller than actually people think. Because when you see a picture of it, you always think it's a big box, but it's actually quite small. So when I was doing that, somebody took a picture of me. At that time, it was with an iPhone 6S from 2017. And it occurred to me a little bit later that we use a device that has tens of billions of transistors to take a picture of a single transistor, the world's first. And this is within almost people's lifetime. Right? This is an extraordinary accomplishment by entities with a brain made of meat. Right? It's an incredible thing. But it has consequences. And I'll tell you why I think it has consequences. So if you fill a room this big with everybody across as much knowledge as possible, the chances are that we will not be able to collectively comprehend how this iPhone works from end to end. I'm talking about semiconductor industry, the physics that goes into it, the chemistry that goes into it, the quantum physics that goes into semiconductor operation, the circuit designs, the manufacturing side, the packaging, the software, the display, the RF, the systems, the cloud, the material that goes into the display. If you collect all of that end to end, we will not be able to hold it in our heads. Now, this is not the first time that our species has made something that a room full of smart people don't know how it works. It's not the first time, but it is the first time where that thing is in everybody's pocket, and it just works. And there's a problem with that. The problem with that is that the magic is gone, right? The awe is gone. And when the magic and the awe is gone, and people just assume it works, that inquisition into figuring out how it works is lost with it, because it just does, it's magic. And that is a problem, because people take it for granted, especially the new generation takes it for granted. And that, we all lose when that happens. There's also another problem that comes with being severely interconnected, right? These are photos that were actually distributed at the time where electricity was becoming a thing and people wanted to put electricity in the roads and on poles. These were propaganda posters made to scare people at the time because it was an unknown new technology. And the more things are magic, the more people can do this. And it's not surprising because this is what the streets used to look like. These are telegram lines. So when you see this, it's not surprising that the image on the left begins to make a little bit more sense, playing on people's fears of the unknown. And this is something that even our industry experienced during the COVID, because there was a conspiracy that COVID was caused by 5G, which is nonsensical, of course. And people were threatened, people were hurt. Towers were burned, and messages like 5G Wi-Fi is bad was written, even though 5G Wi-Fi has nothing to do with 5G cellular networks. It's a completely different technology, and it's been around for more than a decade. So people don't know what they don't know, and that is very dangerous. Every time any aspect of our lives and any aspect of science becomes a political issue, we all lose. We're all damaged. Because political discourse does not belong in scientific discourse. And politics will always subvert the nature of science itself. And it will cause people to have an attachment to a topic without understanding it. And that is very, very bad for our species as a whole. All of our fields of domains of interest, all of the work that we do is one policy away, driven by politicians who are worried about what people say, people who do not understand it. A few policies here and there, and we will hold ourselves back, as we have done repeatedly in other domains. So we do have to be careful. And of course, social media is an amplifier of this. You can go and look for anything on social media to adjust to the worldview you have. And that is a problem, because it means you will never change your mind. And this is a problem I do not need to go into anymore. I'm sure all of you guys know this in full detail. But there's hope in the end of all of that anyway. We used to burn people and witches and women at the stake because we thought they were witches. And then we transformed to burning rocket fuel to leave our solar system. This is an extraordinary transformation. And it's not just because of scientific discovery. Something about us as a species has changed to make this transformation happen. But the fear and the possibility to fall back onto our atavistic tendencies is always there. And we do have to be careful with that. And that's the main reason that I started my YouTube channel, because it does take a lot of time, and it's just a hobby of mine. But I did that because I wanted to demystify, and I wanted to explain, and I wanted to give the gift of understanding. I really do think that the most wonderful thing you can do for another human being, aside from loving them, is teaching them. Because that will stay with them forever. So everything you see in this picture, all those equipments I've taken apart in some way or another. Many of them are available on my website if you want to go dig down and see how they work. And this is a very esoteric field and very narrow field, but nonetheless, people seem to enjoy it and like to continue doing that to give back to the community. It's all not for profit. But I want to make sure that education retains the value it has, because otherwise we are in trouble. The most precious thing you have as individuals, the only non-renewable resource we have as a species is attention. That is our non-renewable resource, because it's gone. Attention is the most precious thing you have. Before I came here, I just looked at the statistics on the channel of how long my videos have been watched. Not clicked on, watched. It's 1.8 million hours. That's over 2 centuries. I cannot think of a more rewarding thing to think that 200 years worth of consciousness has been dedicated to listen to me ramble on. What an incredible thing. So the connectivity isn't all bad, just has to be used in the right way. And I want to thank you again for listening to me talk about all of this. And I'll leave you with a quote from Carl Sagan, a warning that I think we should all really think about. He was a master of putting these words together. And thanks again for the time.
Yep, the question I had was, does the millimeter wave analysis include the integration of the human with the UE, either in your pocket or on your hand, as part of the antenna system? So are you dynamically looking at the receive power from a human holding it to determine how to calibrate the receive side? Because there is such extreme effects with millimeter wave reception.
Yeah, no, certainly. So in a handset, if you've noticed, there's always, of course, multiple antennas, not just one, because you can easily block one. And particularly in an iPhone, let's say, there are 2 sets of millimeter wave beamformers on the phone itself. But these beamformers only have 4 or 5 antennas each, right? So the amount of beamformer you can get from 4 or 5 antennas in one line, they're also in a line, is not that much. But each of those elements is constantly monitoring the received power. And if the beam cannot be formed, if the loss is too much, it switches to the other antenna. If that also searches and it doesn't find anything, if all of that fails, then it falls back into the low band 5G, goes into below 5 gigahertz. And that's the problem. And the other reason that is difficult is because in order for you to be able to really estimate the link, you have to turn the entire radio on. So they have to turn all the antennas on, they're just jumping back and forth, and so they burn a lot of power in the process of doing that. So the searching is costing you at the same time as that. But yes, all of this has to be monitored. In some more advanced systems, you can measure the impedance of the antenna with circuitry inside the chip itself. So you can anticipate if the antenna's impedance is way off from where it was supposed to be because it's covered, so you don't have to turn the entire radio chain on to figure that out. So they basically do that in the RF section without the modem being as engaged, and then they figure out all these algorithms to jump back and forth. But it's a very difficult problem, which is why I said that the industry went after the hardest problem of 5G millimeter wave, which is the handset. The next easiest one is fixed wireless access, right? Where you have something on your desk, or you have something on your window, where it's a 5G, but it's not moving around, it's not being blocked all the time. And then cars are, for example, also a lot easier, because you can have the antenna on the roof of the car. Again, it's not interacting with the people, and it just keeps getting, and then backhaul point to point is the quote-unquote easiest, because everything is fixed in place with high-gain antennas. But yeah, you're absolutely right. It's a big problem. That's why sub-terahertz in handsets for 3GPP, I don't see it being anything that happens soon, because you need to fix the 5G millimeter wave problem first. And anyway, in 6G, there are other golden bands between 7 to 14 gigahertz, which might come online, which are neither classical microwave, but they're also not high enough to be millimeter wave. So it's a nice sweet spot. That could be another possibility.
I'm going to sneak in a question myself. So in this community, we really like to take stuff apart, understand things. If someone comes up with a new proprietary waveform, then we'll try and hack it. But it seems like the road towards 100 gigabits over the air seems pretty intractable. Like if you're not working for Bell Labs or some other big company that has access to network analyzers and stuff that are really high end. Like what do you say to that? Is there something we can do sort of on the low end to sort of participate in that advanced research?
So there's nothing magical about the waveforms, right? So it's just a matter of having more bandwidth. Now, once you have more bandwidth, other things become more difficult, because now your equalizations are different, your ADCs and DACs are different, your DSP requires to process a lot more signal. Depending on what standardization you're on, you're using a different waveform. If you're on 3GPP, you're using OFDM, for example. If you're in backhaul, you're just using a single carrier QAM modulation, right? So there's no FDM, just a single carrier with a big QAM around it, and that's what you're using. So you can experiment with all of these things at lower frequencies. But if you want to, of course, push the bandwidth, and you do need to operate at those higher frequencies, then you need those devices. But put it on your eBay watch list. You don't need a lot to be at 100 gigahertz, right? It's because a lot of 100 gigahertz sources, at least for continuous wave generation, are just basically diodes, right? You're just using nonlinearity. So sources are not that difficult to make. But you can also just work entirely in baseband. A lot of the work done in DSP design and signal analysis and so on is done at the baseband part with the assumptions of the nonlinearities and the effects of high frequency embedded on top of it. Because you don't want to build an entire radio to study what happens in your baseband. And that's normal. So you don't necessarily have to be at those frequencies to do those experiments.
Thanks. Any more questions? You?
Thanks, great talk. I'm just wondering about some of the negative aspects. So we've got these things running at very, very high frequencies, very, very close to our human body. And I guess that last slide with all of the pollutants from the launch invading our ecology, whether we're kind of monitoring that side of the coin as well.
Yeah, so none of the frequencies we use for communication are ionizing, right? So none of them have enough energy, not even close, to damage cellular structures through ionization effects. In fact, you would receive far, far more harm by being in the sun than you would ever receive sitting next to your Wi-Fi router for decades at a time. Just simply because of the fact that there's not enough energy in these systems. But despite all of that, there are strict and well-controlled FCC regulations of what you can do with your transmitter. Where you can put it, how far people need to be from it, how much power you can put out, what beamforming, frequencies you can put out, all of these are controlled. For more than one reason. First of all, because otherwise the network would fall apart if anybody did whatever they wanted, but also because you want to make sure that these things do not put out too much power if they're close to somebody. As I said, if you hold your hand in front of a high frequency signal, you feel the thermal effect. It's a thermal effect. It's not an ionization effect. So everything we've done so far and every study has indicated that these systems, that the way they're distributed, do not have an effect on the human body. If that changes at some point in the future, because you should always be open to any evidence that comes up, it should be taken seriously. Now, having said that, we also have to keep in mind that it's already hard enough to close a link because there is not enough power, right? The amount of power arriving at your phone from a 5G radio is inconceivably small, right? It is so tiny that we cannot close the link. And every watt of power that we burn in a station matters. We have spoken with network infrastructure deployers. They're like, you know what, just give us the same box you had last year, cut the DC consumption by half, and we'll buy it. Forget 5G, 6G, 7G, just cut the power in half. Because it's so precious, because majority of the cost of ownership of those boxes is in power. So believe me, nobody puts out more RF power than the absolute minimum they have to, because it costs us a lot. And because these are non-ionizing, this is the thing that you need to keep in mind is that they cannot damage your cellular structure through what UV light does. I was having dinner with a cancer researcher from the Dana-Farber Institute in Boston, and I asked him, he's a liquid cancer research, basically a blood cancer. And I asked him, how do I avoid cancer? And he said, there's only 3 things you have to do. A, stop time, because time is the primary reason, because mutations take time. Second, so don't go into the sun, wear a sunscreen, and third was don't smoke. That's it. These are you will cover 99.9% of everything else, right? It's either your genetics, sun or smoke, unless you work in a next to radiation nuclear material, it doesn't matter. And he's talking about hundreds and hundreds of thousands of patient data that he has compiled. Of course, I'm not a medical doctor, but what I do understand is the ionization effects, and I can interpret the studies done on biology based on the signal propagation that is done and the energy that we put out. So far, everything points to that it's safe.
Do you have a question? Okay, we have a question over here.
Thanks. So coming back to the MMICs with the massive antenna arrays on top. Well, I'm a software-defined radio person, so how far does, feels like it was a very slow thing, software running on some processor compared to the data rates we talk. Like how close do we actually get with the software to selecting, whatever beam patterns or adapting, or is this all hardware, hardwired, non-configurable stuff?
Yeah, so every phased array, so you have to separate two things. One is what you're allowed to do and what is possible. So every time you build a phased array, you could expose all the controls of the phased array to the software layer. Nothing's stopping you, right? You can program the beam. You can even create beams that are weird. You can defocus the beam. You can make two beams if you wanted to, because you have full control over the entire phased array. That's all possible. It's just a matter of whether the company that is making the array would make those parameters available to you as a low-level hardware to be able to talk to it. But it's definitely possible, because that's what they do in the background anyway. In fact, in 5G massive MIMO system, in 6G massive MIMO systems that one of the things Bell Labs works on, there's all these advanced beamforming, zero forcing, there's all these eigenvectors that they create where they can null one specific person completely while serving another person. They do null steering, they do main beam steering, they do multiple, they defocus the beam, they refocus it. All of these things happen. And if you throw AI at that problem, which people have, you don't even know what beam you have. It'll just pick whatever that works best, right? It may be some bizarre thing that is using some reflections around that just happens to work. That happens all the time. Just like that constellation I showed you, it is something unpredictable. But yes, if you, nowadays with 5G millimeter wave, I'm sure you can go buy prototypes and evaluation boards online that give you complete control of phase and amplitude of every single array. You can do whatever you want, build any beam pattern you want.